And how are we going to read it? We're going to create this little program. This program uses fs read to string, and it gives it a file path, right? So the file path is not specified. We're going to have to fill that out later. But it calls .expect on it. And what do we know of .expect? What does it do? Huh? .expect takes a result, and it says, if I got an error on that result, panic with this string. Right? So we have the opportunity to unwrap a result, which panics if you have an error with the backtrace, or we have the ability to call .expect on a result, and that panics with the string you provided. It's a very simple way of providing more information without actually handling errors. You're providing more information, but you're still panicking, right? So Rust's method of handling errors means you give the people that are calling that code the ability to handle that error. The second you panic, it's game over, you know? So we're still panicking, but now we're giving more information. And we're saying we should have been able to read the file. So in the event we can't read the file, we're going to die and give that error. And then we say with text content. So now you'll see up here they have the snip. Why do they have a snip? Because they probably did it in the last chapter and we may have missed it. Where did they do that? They did it right here. OK. So in this chapter, in the very last part of this chapter, I said we pull off the two arguments. Let's talk about that for a second. You see the first one is query. So the first one is that query argument. That's what we're looking for. And the second one is the file path. That is where we're looking for it, right? So needle, and then the file is the haystack. So we invoke this mini grep. The first thing is the thing we're looking for. The second thing is the file. Now notice everyone here knows what grep is, right? Raise your hand if you use grep and you know what grep is.
I know what it is, but
OK, so 80% of people. Let's go over it then really quick, just so we're on the same page. If I have, if I'm in the temp directory and I'm going to go mkdir, let's rmrf foo. That's interesting. I'm not going to do that because I don't know what's in there. We'll just go to another directory. And let's take that poem. Where was my poem? There we go. So now I have a poem, and I have the opportunity to run grep, and then I can say what I want to look for. Let's say I want to find the word nobody in that poem. I can do grep nobody, and then I give it a path, poem.txt. It's going to search for that through that poem, and it's going to look for that thing we give it, nobody, in that text file. That's what grep does. It's a very basic utility. So we are writing an implementation of grep that is very minimal, right? It doesn't do any of the fancy things grep does. Grep has a whole lot of much more fancy things it can do, like regexes and counting and all that other kind of stuff. We're not going to do that. But this is going to have the ability to run that syntax and print out the output. So that's what we're trying to build here. So grep, the thing we're looking for, and where we are looking for it.
I always thought of grep and regex as inextricably related and linked, but here it's just a search, simple search mechanism within the text file.
If nothing is magical, that's how it works, yeah.
It always seems more magical than that. I mean,
just wiping that magic right away. There are multiple different regex engines that grep has. It has extended regexes. It has Perl-compatible regexes. I don't know that we're going to be using any of those in this example, but we'll figure it out. Maybe we do end up using them. I just wanted to show a very simple invocation of what it looked like. OK, so here's where we're at. Now we know where we're getting file path. File path is the second argument. The first argument is what we're looking for. Second argument is where we're looking for it. And you can see here we're going cargo run --the, which is the first argument. Poem.txt, that's the second argument. We are looking for the word the. It's going to search the entire poem that we've provided it, and it is going to print out all lines that match the occurrence of the word the. And that's what we get. So if that line doesn't have the word the in it somewhere, we're going to get it. Now notice, right now it prints out the entire file. Why? Because we haven't built that functionality. OK, there we go. That was confusing for me. That's what we're aiming for. We don't yet have it. So right now all we're doing is printing out with text contents. We're dumping the entire file. We haven't yet implemented the functionality that does the searching. But this is the goal. The goal is to write this syntax up here, where we can say the poem, and then we just get the lines with that match the. But right now, we're printing out the entire file. OK, so the first step is we've now gotten an ability to parse arguments, and we have the ability to open the file, and now we're going to implement the ability to search through that file. We have different, more or less, stages of this program, units of functionality. And we're going to see how we can break those things off to write better code. So we create this new function called parseConfig. And why do we do this? Well, before we had all this inside of main. But main is not supposed to be big. It's not supposed to have your entire program in main. Main is where you enter, right? So parseConfig is something you could potentially use elsewhere. And it is better to have that in its own unit of code rather than it all jarbling together in main. So we can take that, break it off into a new function, and that's what we're doing here. So parseConfig now is defined to take a list, a vector of strings, owned strings, and it's going to return a tuple of string slices, right? So two different strings are going to come out of that tuple. So notice one thing here. I actually said that wrong. No one caught it. It's not taking a vector of owned strings. It's taking a reference to a vector of owned strings. If it was taking a vector of owned strings, this wouldn't work. Right. It wouldn't work because then it would be moving ownership. So this only works because it's taking a reference to the vector. Does anyone want to explain to me why it only works because it's taking a reference to the vector?
Because it doesn't move the ownership.
Well, what does that mean? That's what I said.
Because when you move ownership, where it was used prior is no longer valid.
Does it maybe go out of scope or something?
It's also related to lifetime, right? So once you're out of the scope,
You can't.
Because the args are immutable.
and you leave a dangling reference in the main program once you move the.
OK, all of these answers have an element of truth to them, right? But we're not really getting the picture here. If the function took a vector of strings and it owned them, it would have to give them back. It's clearly not giving them back. So it's not going to work, because then those strings will cease to exist. Now, you may ask, well, so what? They cease to exist. Why wouldn't that function be useful? And the answer to that is simple. What is the function returning? It's returning two string slices in a tuple. Now, if we know it's getting a vector of strings, and it's not giving the strings back, how can it ever return a reference to anything? It can't, because the only thing it's getting will cease to exist when it's done running. So how can it return a reference to anything? It would be impossible. So we know that by the mere fact it is taking, if it was taking a vector of strings, then it would either have to give the vector of strings back so they continue to live along with the reference, or it would have to not give back references at all, because those references can't be pointing to anything. Yes?
If you cloned it, or no, that wouldn't work either?
If you cloned it and it took the strings, right, you would have two copies. But it's still, if it takes ownership of the first copy and you clone it, you still have two copies now, right? But when you go out of scope, you're going to release both of those copies. You still have the same fundamental problem. You either have to give back one of those copies, and you can have then string slices to that copy, or you have to not give back any slices at all and let both of those copies die when you die. You know? And the way that you think about this is, I'm giving back a slice of what? You know, you can give back a slice of something someone else owns, but you can't give back a slice of what you own. Because if you take ownership of it and you go out of scope, everything you own is dead. It's going to get marked for destruction. And you can't give a reference to something that you're marking for destruction. So the compiler won't even compile that, won't accept it. So that's why when I said I omitted the word reference to a vector of strings, you know, we should have said right away, oh, that's not going to work. So So yeah, it's taking now a reference to a vector of strings. Now I'm saying reference to a vector of strings, which means it doesn't actually own the string. Someone else owns the string. And it's going to give back two different string slices to one of those strings that someone else owns. That works. Because someone else is responsible for the destruction of that string, and Rust will simply pass back the lifetime and say, as long as that string lives, as long as these lifetimes, we are good. All right. And in this case, we know how long that lifetime has to be, right? It's going to be assumed that these two string slices here have to live at least as long as the reference to this vector of strings here. That's the rules. We know that because Rust didn't make us annotate that. So this goes through one of those 3 lifetime elision rules we covered in one of the earlier chapters. Right? Now I forget the ordering of them, but it's one of those 3.
But you can make that explicit with tick A, right? Like tick A, then tick A apple.
You could make it more complex, yes. Yeah. Grouping configuration values. So now we have pulled out this parse config thing, right? And how else can we break up this program or make this program more modular? Well, one method we can do, and by the way, this is the method that Python does, and also the method that Rust does. Let's take a look at this right here. It's called parse args Python. Let's arg parse. That's there we go. Yes. So in Python's arg parser, you create an argument parser object, and then you call these different methods to add what you're looking for, right? This is looking for a thing called integer, and it's of type int, right? So in Python, you create an argument parser by calling these methods on it, right? In Rust, we create a config object, which has in it what we need to configure our application, both the name that we're going to be providing in query and the type string. So we're creating something to hold these types manually, this config object. Then what we're going to do is populate that config object with parse config. So parse config is going to take this vector of strings, a reference to a vector of strings, and now it's not going to return a tuple where you have argument 1 and argument 2. It's going to return a config object for you, right? Now, in my opinion, this is still not ideal. Why? Can anyone give me an idea? We went through this before. I said, I don't like this pattern. Why is this not a good pattern? This is not something you'd see in professional Rust code. The reason is we have something called parse config. I'm just going to, this is nothing the book is going to say. I'm just telling you like how we see bad code and good code and what we look for, right? This is ranty, but whatever. We have this thing called parse config. It's taking something, and it's returning config. Now, what do we call anything that takes an argument and returns an object?
Function.
F. Someone smarter. Takes something and returns an object.
Constructor?
Constructor. Boom. Right? So this is a constructor. It's just like new. Right? New can take whatever. This is taking a vector of strings, and it is returning a reference to a vector of strings, and it is returning an object. I would take this parse config, right, and I would implement it on config. I would say implement this on config, and I would say from underscore config, or from vector of config. And then, rather than returning config, you could return self. And now, parse config is a constructor, and it is implemented on the object you're constructing. So the whole idea here is about modularity, and you want this to be tied with this. They have to come together. This doesn't make sense without this, and this isn't useful unless you have a method of constructing it. You have some place to put the code to construct it. So I would say put this as a constructor. The book didn't do that, so this isn't the first time they've done this. Yes?
Like actually typing that out, or like having an example of that.
Yeah. OK. So let's take this code. Put it on. And I'm going to do cargo new. And we're going to call it hlug arg. So we have something like this. And I wish they didn't snip me, but they snipped me. Failed to resolve. Oh, here, we need to go here. Use std-env. And are we ready to run this? Use stdfs. And are we ready to run this? And now we have contents, and we're not doing anything with it. So let's do something with contents. OK. And now the problem is we need to provide the arguments. So this is what we're looking for. We're going to say needle and then poem. OK. So now that's how the program's supposed to be run. Now, here's what I would do. This parse config thing, we can go implement impl on config, and I can open this up. I'm going to copy this function here into config, and I'm simply going to rename this and say from vector config. Now I'm going to indent this. I'm going to come down here, and where we used to have parse config, I'm going to simply say config from vec config. That's it. That's a huge step, in my opinion, in the right direction. Got it? And now, by the way, this has one added benefit too. You can come down here, and where we have this, we can say self, and then I can come down here and say self. So you don't have to actually call your objects by name. It can figure all that stuff out. I like that. The other advantage to this too is if you have 10 different types of config objects, they can all be constructed with the same constructor name. Every different config object will have a different name for that object, right? So if I come down here and I want to say another one, let me give an example. Let's say that we have now a different form of config object. Oop. Well, I want the whole thing. I don't want just one. There we go. Now I can say here, rather than this, I'll say config foo. And now config foo, the only thing that's different is he has a different name, right? So now I have two different functions here called from vec config. Why is this color so horrible? As God intended. I have two different configs here, config top and then config foo. You see them? The one at the very top of the page, and then this one right here. OK, and both of these different structs, they're named differently, but they're both constructed with the same named constructor. This is only possible because the constructor is implemented on the struct. Previously, we had a function called from parse config. If I have two different types of config objects in that program, I'd have to know which one of these config objects is from parse config going to return. Now I explicitly know. If I call config : from vec config, I get the one at the top. If I call config foo : from vec config, I get the one at the bottom. It's another advantage. OK?
Thanks, Xavier.
Not a problem. Anytime. OK, so now they're going to rant about clone. Bottom line, we already went through this. Clone makes things easier for you as a programmer. It makes them ever so slightly more difficult for the computer. But I wouldn't worry about it much, because by the very nature that you're using Rust, most likely this will be the easiest for the computer it's ever been. It's substantially more efficient than Perl, Python, Ruby, PHP, Go, all these other types of languages. If you use clone, don't sweat it. However, there are some trade-offs. It's not ideal. Here we have a function at the top, and we're declaring args as a vector of strings. And I'm saying from the environment, collect all these strings. Now we're doing this. Oh, OK. So now we've done it. We moved the parse config into the new thing here. So now we've done it. Now, rather than our from vec config, they simply call it new. Good. Improve the error message. Okay, so now we get down to the question of what happens if we don't provide the right amount of arguments to our new function. Because new takes a vector, and vector in Rust is unsized, right? So we don't ever know the size of the vector in compile time. It could be however big it needs to be. So how do we assert that we are receiving the right size? One thing we could do is we could use new and then say if args is less than 3, which means it is 2 or 1, then we're going to panic and say not enough arguments. Why? Because remember, the first argument is the program name. The second argument is what you're looking for. The third argument is where you're looking. So we're saying here if we have less than 3 arguments, panic. If we have 0, 1, or 2 arguments, right? It's almost impossible to get 0 arguments without deep hacking, but sure, you could do it, you know? So, and we have this problem here. Now we run cargo run and we get this panic. Now, what do we know about panicking? We know we don't want to do it, right? We should know that much at this point. This is not our first rodeo here. So what is the right way to do this? The right way to do this is to have your constructor, because it can fail, return a result. That is better than having a constructor that always succeeds with an assumption that may not be true, right? So because we have an assumption that may not be true, it is better to return a result in the event it's not true. And that's how we can do it. We can do it by returning a result of config rather than a config. So here is one method in which we can do this. Now we're implementing a thing called build. Build takes a vector of strings, and now build is going to return a result of config, which is the success case, or a reference to a static string, which is the error case. Now a reference to a static string means that the string will live for the entirety of the program. So when we declare this here, return error, not enough arguments, we're effectively saying that that's a static string, it's going to live forever, and we're going to die, right? So that is one method in which we can do that. Config build unwrap or else. OK. So now we have something that is potentially returning an error, right? How do we use that error in the event it errors out, right? One of the methods we can do is match it. So far, that's been the big one we've seen. We match on the result, and one of the match arms is OK, and the other one is error. That's how we've seen it in every occurrence thus far. We either do that, or we use the question mark, which says if we have an error, give it to the thing that called us. Otherwise, unwrap it, take the result. That's how question mark works. Now, here's the thing about the question mark in Rust, though. The question mark in Rust doesn't work on main, because main doesn't return a result. So it has no one else that you can bubble up to. So in main, you have to handle the error. And how do you handle the error? You do this. You can say something like this, unwrap or else. Now I'm saying effectively the buck stops here, I can panic. Main is the one function where people will argue it's OK to panic, because there's nothing left to do. If you can't handle the error by the time it gets to main, it's time to call it quits. And that's what we do. We panic, we print the line, and we exit. Actually, let's take a note here. Let's actually correct that. I said we panic, we print the line, and we exit. We don't actually panic at all. So they're calling println exclamation point. The first time I read that, just because of the nature of the context and where it's at, I figured they were just calling panic. They're actually returning they're returning exit code 1. Right? So they're saying here, print the line to standard output, and then exit with 1. Right? Now, if you don't know the significance of exiting with 1, in Linux or Unix or any of these like not Windowsy things, your success code is 0. Anything that's not 0 is an error. That's how it works. So when you write ampersand ampersand in the shell, you do something like this thing, ampersand ampersand, this other thing. What it actually does is it says, did the thing on the left return a 0? If so, execute the thing on the right. That's how it works. Here we're doing the same. We're telling it effectively exit with 1. That's going to tell right away that there's a shell error. So if you want to see an example of that, if I open up the shell and I do something like echo foo, now I have the word foo on my screen. And if I go echo this, I can see the result is 0. That's the exit code is 0, right? But if I do something like this, Perl E, and I say die 42, that's just a Perl way of doing it. Now you're going to see my cursor went red. That's my shell indicating to me that there was an error. Now if I do this, you'll see that I get a non-zero status code. Right? That's telling me that Perl exited without success. And everything has that in Linux, or everything should have that. They should have success is 0 and everything else is an error, and support that convention. It's a very strong convention. OK, extracting more logic from main. So now we have this main program, and we say we're searching for, and we're getting the config dot query. So we're saying the snip, the thing above, is what is getting us this config object. It's calling that config new, right? In our example, I wrote it as config from vec or something like that. They called it config : new. So they're calling that, and then we are now printing out what's in that config object. So the config was constructed with this vector of strings, and that's what built it. And now I can just access the thing inside of it. I don't have to parse it out myself. The config object contains the logic to parse and build a config from a vector of strings. Now I'm just printing that stuff out. Underneath it, I have a function called run. Run takes the config object, and it opens up the appropriate file. That's all it does thus far. How does it open up the appropriate file? Because run takes the config object, it can call config.filepath on it. It can look at the public property on that config for file path. So now we have seen what it looks like to return an error string, right? But there's something better than that we can return, which is this box of din error. This will work on any kind of error in the standard library, or any type of STD error, right? So this box of din error is somewhat popular. And we're going to see how that kind of works. This std error, I'll show you what that looks like here. rs std error. OK, so this is a trait, and it provides these methods. So when people have an error struct, they can implement this on that error struct, and then it will work with anything that implements this standard error trait. So we're gonna return that. OK, so right away this will not work. Why? This will not work because run returns a result, and we did not do anything with the result right here. So in this part of the code up at the top, we call run, which is returning a result. And Rust always makes us handle the result. It will not compile otherwise. So how do we handle the result? We can either match against the result, again, handling the error and the OK types from that result, or we can simply assign it to the underscore, which says I don't want to do anything with it. This is what I identified as, in an earlier class, being explicitly stupid, right? This is how every other language behaves. Generally, you don't want that behavior. Generally, you want to be explicitly smart. You want to handle the result type and the errors that could arise. But if you want to ignore them, Rust doesn't fight you on it. You just have to tell Rust, I want to be stupid. And you can say to Rust, I want to be stupid, by assigning that result to a variable that never gets used, which by convention is an underscore. Then Rust will simply drop that variable. It'll go away. Rust won't warn you that the variable is never used again because it's an underscore. It's what the underscore means. And now you're telling Rust, I just want to ignore that. I don't care what happens. Rust does everything in its power to make sure that the default is you must care. But if you don't want the default, it makes it very easy for you not to care. And it does that while being safe. Nothing bad can happen from you not caring about whether or not it was a result or a failure. Right? That's not something that has to do with the type safety of the language or the memory safety of the language. It's just good practice that's built into the language.
Is that a code smell?
It's not a code smell, because a code smell would imply that it is a warning, right? Generally speaking, we don't say code smells for things that would stop compilation.
What's a code smell?
A code smell is a violation of conventional practice, but I've never heard code smell in a context where it will stop compilation. You know? Yes?
Besides accept, could you just do the unwrap and it also would be like handling your error?
Yes, unwrap will panic, but it won't panic with the string that you provide it. So if you don't want the string, you just want the backtrace, you can simply unwrap. Yes. Yeah. Actually, I was wrong. It doesn't actually stop compilation. Yeah, I was wrong on this one. It's just a warning. So yes, this is a code smell. I'm cool with that. Yeah, this is a code smell. Russ is telling you that you're violating the code smell. It says, yeah, unused must use. That's the thing that you're violating. And it tells you here you can actually disable this. This is on by default, but if you don't want this, I think you can say, what is it? I mean, I'm working on a Rust project right now. I disable a bunch of things while I'm developing Rust. I disable allow. Yeah, so you can say allow, and you can say unused must use, and then it will actually disable that code smell for you. Yeah, cool. I don't ever do this, by the way. I don't think I ever use let underscore equals, except maybe in development, just as a quick hack. So yeah, I'll always handle my stuff. And that's also kind of interesting, you know, that the more senior you are when you're programming, I would say, the less likely you are to care about warnings versus errors. You know, generally speaking, I want clean compilation any language I use. If you write C code, you write in the latest standard revision of C, and if I get any warnings on GCC, I go in and I fix those warnings. I don't want to disable them. You know, so GCC has like WAll or whatever you're writing in, and that tells me complain about anything you see a potential error in, and let me go back and fix it. And that's what I try to do. But yes, if you want to ignore it, there's a method of ignoring it. Splitting code into libraries. So we have this method right here of, now what we're doing is we have this config object, and we have got this build inside of it. And notice build is effectively a constructor. It's returning a config object. The only difference is it can represent failure in that construction. It represents failure with a static string. And then we have a run method. It takes the config object, and it returns a result, which has nothing that represents success. It's a tuple, a unit type. And then the result has a potential error side of a box that implements this error trait we just took a look at. Let's talk about both of these things. From my perspective, if you have run, which takes a config object, you may as well implement it right on config. You may as well say config implements run, and it takes a reference to self. And then you can do everything with it, right? Here they have chosen to show it external. I don't know if they're going to pull it in later like they did with build, but they could. Here is one method of handling the error object. So we talked about you can assign it an underscore, ignore error and result. Here is one method here of handling the error object using if let. Remember, if let is like a match with just one arm, where the other arm says accept everything and do nothing, right? So if let says if I get an error of E, then I want to do something with E. I'm unwrapping the error. I'm taking this E, whatever's inside of it, and you can do something with it. So this will handle that. OK. I'm going to get a soda, and then I'm going to come back, and we're going to talk about this stuff. And then, by the way, this is probably like very opinionated. It's a little controversial. How many people in here have heard of test-driven development? Does that ring a bell for anyone? OK. Raise your hand if you like test-driven development. OK, so we have, this is exactly what I would expect. We had 4 people raise their hand. And then I said, how many people like it? And 2 people raised their hand. And that's why it's a gigantic holy flame war. I would have had my hand down on the second question. This is not an area I like. I will make sure my code has no compilation errors. I don't care about Rust style. And I don't care about test-driven development. But I will say that Rust makes test-driven development way the fuck easier and more convenient than any other language, right? Because you can write your unit tests inside of the same file as your code, and it's encouraged, right? It's encouraged because there is zero downside to it. It's interesting because I'm actually building the ability to do this for other languages right now. That's actually the project I was just showing you was, this is a pod parser for Perl. It's a documentation framework. So I'm building essentially a pod parser. By the way, does anyone here use Perl other than me? No one? No one ever used the Perl? Okay, it's a fucking old language, but it has documentation inside of it that is written in a really archaic format that only Perl uses. The whole rest of the world is Markdown, but Perl still sticks out like a sore thumb. It uses this thing called pod. What is a line-based format, and I'm building into that documentation format the ability to build doc tests, you know. So what I was going to say here is the test-driven development is a philosophy. I don't think that has any place in a book, but because it's always very divisive, but a lot of people disagree. The idea of test-driven development is you write the test, and then you make the tests pass as you develop your code. So rather than developing your test after the code is done, you develop the test before you write the code. And the tests are effectively front-loaded. So before you start writing code, you write the test for the interface you want to build, then you build the interface, and then you make it pass the test, then you move on, you write more tests, you build the interface, then you write the implementation to make it pass the test, and you complete this task on and on and on. I will say this about it. There are two different ways to develop code. Now it's a spectrum, but there's two different poles of code development. There's one, it's the bottom-up approach. The other one is the top-down approach, right? The top-down approach means you have an idea of what your final product is going to look like. And the bottom-up approach is you keep building in the direction you want to go. And then because you never have a place where you say, I'm done. I'm never going to write another line of code on this project. We start from that point, and then we keep evolving that project until it gets to have the functionality we want. And in this process, you have much more exposure to code creep, right? But you also have much more, I would say, versatility and adaptability in development. You can say, I don't like the way this is working. Let me change it. With test-driven development, it's always more painful to do that. Now you have to go back and change the test before you can update things. But this concept of writing tests first is something that I would say is better done in Rust than other languages. But here's what it looks like. Here they're implementing this module called test. We've already seen this. We've seen how it works. We know how assert equals works. We know what the vector works. We're building this test, and it simply fails. It fails because we don't have a function called search. So we are building a grep program. Reiterate. First argument, what you're looking for. Second argument, where you're looking for it. They are saying in this test that we're going to implement a function called search. It's going to take two arguments. The first argument is what you're looking for. The second argument is where you're looking for it. And a block of text, right? This is a test for an implementation of search. Presumably, because of the context, we're building a function called a program called minigrep. This is going to be the workhorse of our program. They have a definition for how it works. It is as such. This vector, safe, fast, productive, right? This is going to produce a string vector that has that inside of it, a string slice, a vector of string slices that has that inside of it. And we want that to be the same as search for query result. Now, what is query? Query is up at the top. It's duct. Right? What are the contents? The contents are this. If you notice, the word duct is right here in the middle of productive. So they are effectively saying, when I search for the word duct in those contents, I want it to be the same as the vector of string slices, safe, fast, and productive. So our search is going to return a vector of string slices. And in this specific example, there's only one element in it, which is that one line. Potentially, if I was doing a search for the letter U, right, it would return this line in the vector, and it would return this line in the vector because there's a U in productive. It would have 2 entries. But ours only has 1 entry because we are searching for the word duct, which only exists in the middle of the word productive, which is only on 1 line. Does that make sense? This test fails because we haven't implemented search, but we wrote it first. Now we're going to implement search. Now, what's cool about it is that it is in the same file that you're going to implement search. You don't have to go somewhere else. That is, in my opinion, a huge boon towards test-driven development. I don't have to open up discrete files all over the place to make it happen. I, generally speaking, don't know how my program is going to look in the end. But I don't think it's unreasonable. It is far less unreasonable for me to be expected to know what the file structure of my program is going to look like at the end. I could say I have 1 file to parse the arguments. I have 1 file to do the searching implementation, whatever. I could say that in the beginning, and I'm probably not that far off in the end. Everything may look different. I may change the API, but the directories, the folders, the files that are inside of it, all that other kind of shit, that is pretty high level. I could keep that the same. So the fact that you're writing these modules of test next to the code is advantageous. Now, we have this function that doesn't exist called search, which is right over here. And now we're going to start by stubbing out that function. And stubbing out the function means we're going to implement the types that it takes, the types that it returns, and that's it. That's a function stub. Now, this is also not, generally speaking, how I write Rust code, or most other people that I've seen. Because we generally stub out the functions not by putting an empty type in there just to make the type signature pass. That is not useful functionally, right? We generally put the word to do in there. To do exclamation point. I'll go back to the Rust code, which is all going to be open source anyway. I'm just not ready to release it. And if I look here in this program for to do, you'll see I do this all over the place. These are all stubbed out. Right? This is an area where I'm writing a parser for a documentation format, and I'm saying if the command is pod over head, begin, cut, I'll handle it later. That means I haven't written any of the parser yet. I'm just writing the other stuff around it. And I stub it out with the word to do. That's much more typical. If you want to write a stub for a function that's never implemented, and you don't have any intention of getting back to it, you can write the word unimplemented in there. And Rust will handle that. And they all take strings that'll trigger and panic in the event you hit them. Right? Now, before I finish this code, everything except the top one I'll implement. And I actually wrote that there, unimplemented. Right? So Perl has a documentation format that has different encoding. If you tell it you want any encoding other than UTF-8, you can fuck right off. No, I'm just not going to support it. It's just too much work. So I just write unimplemented there. That one, that's not a stub, right? So there is a distinction there between a stub, to do, and unimplemented. I'm never doing it. Cool. And I lost my page, so give me a second. Yeah, here's our search. OK. So now we're doing cool. Cargo build. OK. And it's telling us, OK. Let's take a look at that one more time here. So we have a problem here, right? We've defined search in a method in which we're taking the lifetime of A, and we know contents has a lifetime of A, and vector is returning a lifetime of A, but we don't identify string, right? So that is creating this error down here, right? We have an expected named lifetime parameter here, and we're not providing it. So what they want is us to have all of the lifetimes explicit. What they're telling us is effectively that this lifetime in the end, the lifetime of the string slices that search is returning, they either have to live as long as the contents, or they have to live as long as the search term. Does that make sense? You're giving 2 different strings to a function, and you're returning a string slice, a part of one of them. The thing is that you're returning, you have to say, does it live as long as the contents, or does it live as long as the search term? After you use the search term, you're not returning that. You're done. You're using the search term to find the lines. The lines have to live as long as the contents. So You could do this. You could say they must all live the same length. That is stupid. That's a bad suggestion. What you should do is say that the return must live as long as the contents. So you would normally say tick A, tick B. Tick A would go to query, tick B would go to the contents, and then you would be returning a vector that must live as long as the contents, tick B. Okay? That's how we think about that. And this is where the power of Rust comes in. You know, you're telling it which one of those two things you're providing a slice into. And then Rust will figure out when the contents go away, everything you return must go away too. And if it doesn't go away, and you're telling Rust it must go away, then Rust will come back and say, I don't compile that. It'll give you an error in compilation. OK, so now we're writing code to pass the test. So we have this search implementation here. And again, this is, in my opinion, not done right, because we don't differentiate the query from the contents. But whatever, we have this for line and contents line. And then we say do something. Now we're going through each line, and we need to find some method of matching, right? And we got into that thing earlier with Robert. He's in his own world. But we talked about the terms that you're giving grep, which could be a regex or a literal. You could say, I want to find this pattern, or I want to find this literal string. And this search implementation has to decide how it's going to handle it. Is it going to accept a pattern? Is it going to require a literal string? We don't yet know which direction they're going to do. So we're saying if line dot contains query. That's what they've decided to do. Right? So now if we want to find out what dot contains does, what do we look for? Who wants to hit this up? OK, I'll tell you what we do here. We have this thing called contents, right? Which is a string slice. Contents is used in contents.lines. So we have dot lines, which works on a string slice. So we can come up here, and I can go rs, and then I can say str.lines. Oops. What's the right syntax for this? Nope. I don't remember the right search extension. It goes, let's take a look. No, what is the right way to look at the primitive std? That's what I want. No, let's see here. I'm not using my search extension right. So come down here. Search functions, methods, and macros. That's what I want. Search Rust C docs. That's not what I want. Mod struct enum. OK. Let's just try this here. String. This takes me to, that's not what I want. What is the right syntax to get this to work? Not the crate for string. So they're just typing it in, thread, and it's bringing up the standard for thread. Well, what was that? Why did I see that? Damn it, you're moving too quick. str. That's it. They just typed in str. Why doesn't my str do the same thing then? My str takes me here. What the hell is going on? They're typing in the same thing in that graphic. Rust search extension, str. Are they doing tab or something afterward? rs space str. I don't understand this one. I don't know. Someone broke it. Yeah, that doesn't work either. So I don't get what the hell am I missing here? Search docs. Okay, I could just use Google. That's interesting. I don't understand how that broke. That seems like the most basic functionality ever. Search built-in attributes, derive. Can I use, question mark, help, cargo, yet, book. Okay, anyway, I'll have to look that up. So here, I'll just go down here, rs, rust, string slice, lines. There we go. That's what I wanted to find. std str lines, is that what it wants? Oh. No, it's pulling up create lines. I don't know. I'm gonna have to look that up. I don't know why it's not working. Okay, so function lines. Lines on the string is gonna return this lines deal here. And that's what we're calling, right? So if I come back down here to the book, sorry about the distraction, we're calling contents.lines, which is gonna return this thing, destructive lines. And then what we're calling on it is .contains, right? So whatever this is returning, we get to call .contains on it. So this is, okay, this is returning, I think, an iterator. And what is the item in the iterator? That's not useful. Okay, this is returning lines as a string slice. So if we click on this, now we're in the primitive type string. And now we can say here contains. And this is going to be the exact code that we're looking for. So this is what our search implementation is using under the hood. Public function contains. Returns true if the given pattern matches a subslice of the string slice. Returns false if it does not. This pattern can be a string, a character, a slice of characters, or a function or closure that determines if a character matches. So we call .lines. It's going to break apart the content by new line. Then we see if the line contains, and we've just read the implementation of contains, the query, which is a string slice. So it's going to be implemented using contains just like this. So does bananas contain Nana? If the answer is yes, that is true, right? If the line contains it, we're going to get a Boolean back, and then we can do something with the line. Now we know we want to return a vector of strings, of string slices. So what we should do is create the vector of string slices and then push onto that vector this, the line, right? And that's what we're doing here. We have this let mute vector equals vector new at the top. And then we call result.pushes line and we return it at the bottom. Now what's kind of interesting here is that we don't define the type of results. Rust figures it out. Why does it figure it out? Because we always have to write the return type and the input type of the function. That has to be done. So because we know the return type of the function is the vector of string slices, it knows this is a vector of string slices. And because it knows this is a vector of string slices, it can simply infer, we went through that before, type infer the results at the top. Note, this is not meaning it's loosely typed. It's strongly typed. It figures it out in compile time with 100% certainty. So that's how that works. And now we're going to have this results, which is a vector of string slices. And then when we run it, you can see now we have this search implementation. We're passing our test. Running one test, the test passed. So we wrote the test first, then we swung around and we wrote our implementation of search. Now we have an implementation of search. We need to implement it in the function. So we go back to our function, which is run, and we use it right here. For line in search, and then I'm looking for the config.query in the contents, right? And where do I get contents? I get contents right here. So I am taking a config object, which has in it a file path, I am opening the file path and retrieving the contents using read to string. Then I am using our search procedure to search through those contents with the query, which is parsed from the options you started the program with, the config object. We saw that earlier. And then here now we say cargo run frog poem.txt, and we're looking for the word frog, and it says how public like a frog. That must have been a line in the poem. So how public like a frog. That's the line it's returning. All right. So when we search for a word that doesn't exist, like monomorphization, that doesn't exist in our poem, thankfully, because that word doesn't exist in our poem, it returns nothing. There's no lines pointed out to the screen. And that's the same way that grep works. If we grep for that, I'm not going to try to spell it, and everyone will laugh at me, we get nothing. Now we'll notice one thing that grep did is it returned 1 because it didn't find it in the file, and we'll also notice that we do not do that. So ours just returns success. So that doesn't exist. There's a slight difference there, but that's it. All right. Now we need to work with environmental variables. So what do we do to work with environmental variables? We have 1 hour. We use a new thing. Well, we're writing more tests. I don't know why the chapter is called. OK, writing a failing test for the case-insensitive search function. So we're going to make our search case-insensitive, right? We have a case-sensitive search at the top. This handles this. And then we have a case-insensitive search at the bottom. This is going to handle, regardless of search, it's going to find it, right? So in this copy, right, we're going to have to implement a whole different implementation of our search function that is going to look for just, it's going to look for the match regardless of case. So that's where we're at now. So we have implement the search case-insensitive function. Here it is. And this is just another implementation of a search function. In this one, rather than using contains, we simply call lowercase, right? So we're going to lowercase the query, and we're going to lowercase the line. So we're going to do a lowercase search of this. Now, this will work, and it will be, let's take notice of one thing here. We are calling to lowercase on this line, right? We are pushing line here. These are not the same line. To lowercase, I don't believe, is a mutator. We can look that up. Actually, we know it's not a mutator. Otherwise, we'd have to say for mute line. So I don't have to look that up. Russ tells us. So we know that to lowercase is actually, under the hood, taking our line and then making a clone of it and lowercasing that clone. We know that. And that's important because if we were lowercasing our copy of the line, then the results that you were returning from search would always be lowercase too, and we wouldn't want that, right? We want to return the original line and just search in a case-insensitive fashion. OK, so now what we have to do is we have to know when do we want to use the insensitive search versus the case-sensitive search. And we do that by adding to our config a new thing called ignore case, which is a bool. So now we're going to go back. By the way, this is bottom-up design, right? So we had this chapter here about test-driven design. And if you were implementing all of this stuff as you're building your program, you could get to the area where now you're changing the implementation. Like they very cleverly created a new function called case-insensitive search. But what if they were to take this bool and add that to the current function? Well, now you change the prototype of the function. You've got to go update your test. So the reason likely why they created a whole separate function for case-insensitive searching rather than doing it in the same function is likely because they didn't want to go edit the test. So they're trying to ingratiate the test-driven design people by not having to go back and edit the test, which you always have to do when you adopt this method of development, right? So public struct config. Now you're taking this query string, file path string, ignore case, bool. And now what we're doing is in run, we're doing this, right? So in run, we're saying if config.ignore case, do this, otherwise do that. in my opinion, that's a little awkward. You may as well just put that into your search function, right? And then run doesn't have to say, if I have the bool, do this. If I don't have the bool, do that. You could put that in the search function, how you handle those elements of searching. OK? And then we have build, and we're giving it the build thing. Now, I want to point out one more thing here. And that is that this run, we went over this earlier, right? And what I said earlier is I would not implement run like this. Because how would I implement run? Run is taking a config object, which has all of its arguments in it. That's the only input to run. And when we wanted to provide another argument to run, what did we do? We added it to the config object. I would implement run as a method on the config object. The config object supports running. And it takes the arguments in the config object, it does something with it, it returns a result. They have chosen to implement run as a separate function. I don't understand their design considerations there, but there you be. What?
You might have a JavaScript.
Yeah, I have no idea there.
Because in JavaScript, you're just passing around a bunch of JSON structs. And if you made it a method, then you have to update. You have to sync up both the server and the client side to the same class.
One could speculate. I'm sure there's 1,000 different reasons we could come up with, but the bottom line is I have no idea. I'm just telling you how I would do about it, doing it.
The way he does it this way, you don't have to sync the client and server methods at all. You can just update the server run. You just update the server run function without worrying about syncing up the client.
Well, but I mean in Rust, if you're taking args, right, and args is these three things. If you have a server and you're communicating with it, and you have a function in the server called run, and it's taking config, and you change the arguments, the definition of config, that's going to change your program. You're still going to have to update the server. You have to update the server now to.
It's a struct with no methods.
But you have to be able to accept one more thing, ignore case. The server would have to do that.
That's just a function. That's just a separate function file. You have to update. You don't have to update the JSON struct, the config struct class, the struct, because you're not adding any methods.
You're adding a new field in it.
Oh, you mean the ignore case?
Yeah, the ignore case is a new field in the J.
Okay. If the client doesn't care about the ignore case field, so it doesn't have the right.
Yeah, but your argument is the server wouldn't care, right? And I'm telling you that at the very least, the server would have to accept that in the JSON.
You update it, but you don't have to worry about updating the client. The client code to be the same definition.
I'd have to think about that. But anyway, we can go over that later. So we have this. We've updated the thing. Now we're doing the stuff. And here's what we got. We have this build. And now build is actually pulling out ignore case 2. So before build was taking out these two different variables, what we're searching for, where we're searching for them. Now it's taking out the third variable, whether or not we want case sensitive or insensitive searching. It's going to return the new config object, which has all that shit in it. So we've now added that field in the object and pulled it forward. Now they're going to provide another method of doing it. So before we were passing these arguments on the command line, but now we're not. Right? If we come up here and we look at it, these two come from the command line, args1.clone, args2.clone. This one, ignore case, comes from the environmental variable ignore case. So all that stuff is getting put into this config struct, right? And it is looking at environmental variable ignore case. So here's how we run this now. We provided the environmental variable ignore case. We say cargo run, the search term 2, the poem.txt, and everything works. Any questions? Writing error messages to standard error instead of standard output. All right, so far we've used println to write to standard output. Does anyone know what standard output is? Raise your hand if you know what standard output is. Looks like less than half, certainly. OK, so every program on Linux has what they would say are 3 different streams of data. The first stream of data is called standard in. That is where the program is going to be receiving input. Generally, when you're running a command line program, it's coming from the keyboard you type on. The second stream of data is the output stream. It's standard out. That's going to print it to your screen. That's your second stream of data. The third stream of data is standard error. that is going to print it to wherever the error is getting directed. So in Linux, you can redirect your error to a different place than your screen. Usually you want that going to your logs, right? Or you want it going to your logs and your screen, right? So you can set up these streams to go to different places, and that's how it works. So you decide, is this an error? If it is, send it to standard error. Otherwise, send it to standard output. And that little distinction is one of the very few that is available to every program. Standard input, standard output, standard error. It's part of the POSIX standard. Every Unix or Linux system uses it. So they're saying here that now we're going to see how to print a standard error. And all that we do is add E to it. In other languages, this is a little bit more complex. But we have println, send it to standard output. Eprintln, send it to standard error. And that's it. OK, this is a different chapter. We're done. OK, that is all the new material we are going to cover today from the book. I'm going to go in and I'm going to rant about how we actually do things. So does that sound like a plan? Does anyone have an interest in seeing that? If you don't have an interest in seeing that, this is slightly more, I mean, the book would probably think of it as more advanced, but I think of it as more simple. Then by all means, you may want to dodge out. But I think we're going to geek out. I had a lot of requests for that kind of stuff. So let's start off and talk about Rust's alternative to arg parse in Python. Right? So Rust has something called clap. And clap is better than arg parse in Python. Bold statement. Let's take a look at it. There we go. At least that's not broken. If you prefix it with exclamation point, it takes you to the crates.io version. That's one of the very few things I use all the time. And I always have that up. So what is really nice about it is look how simple and beautiful that is. Let's take a moment to look at all the shit this is doing for us. We have a struct here called args. And there's a name in it called string, right? And then we have something down here called count, which is a U8. We have a struct with these two things in it. All we have is the name and the type. All of the rest of the code, Rust will generate for you using clap. So everyone in Rust that starts a program that is of advanced or intermediate level will never use the standard library to parse arguments. We will all use clap. It is the arg parse for Python. And what we're going to do is we're going to derive up at the top parser. And parser is a macro from clap. And parser implements the entire parser for you. And the great thing about it is all it needs is the definition of the struct. So the definition of the struct is used in compile time, provided as an AST to this thing called clap, this library called clap. It takes that and says, from it, this is what I need to generate. Now, from the struct alone, it doesn't have enough information. So what does it do? It says, decorate your stuff a little bit. Tell me a little bit about how this is, so I can generate better code. What kind of things are we generating? We have arg short and arg long. What does that do? Arg short means I want to have -n for name. Arg long means I want to have --name for name. You give it that, and it will generate you the option for it. Below, we have short, long, and default value t equals 1. What is default value t? It means if you don't give me anything, I want to default it to 1, and it's type safe. Right? Does it all in compile time. So the default value for count, if you don't provide a count as an option, will be 1. Your users don't have to know anything about it. It's an optional argument. That's a lot of stuff that it's doing for us. And all we're doing is writing a struct on it. Now, I would make an argument. This args looks just like the shortest struct you can make. There are 4 added lines to it. And all of those lines to me are very transparent in what they're doing. Let's compare that to Python, which is supposed to be higher level. Python isn't compiled. We're lower level. We have direct access to memory. Python doesn't. We are supposed to be a lower level language. But here, we have a higher level abstraction. That's a win-win. That's one of the powers of Rust. The Python method, look at that. We're using all of this shit here, which is totally unique to argparse. And by the way, I'm not shitting on argparse. This is better than get-opt long if you come from C. It's better than the Perl way. This is one of the best methods for any dynamic language for parsing arguments. It is actually very powerful. But all of the syntax here is unique to argparse. They were not able to use any pre-existing knowledge in the process of creating an argument parser. Rust was. Rust says, you create the struct and I'll fill it in for you. Create the struct just like any other struct. Python says, you have to tell me what kind of type you're using here. Now, why? I don't know. Python actually has now type annotations. Argparse doesn't use it. It's lagging. It's got this nargs thing. What the fuck is that? That's not a Python thing you see in a bunch of other places. I don't, you know, we can look into it and see what it does. I just like metavar n. Have you ever seen another Python function with an argument called metavar? No. This is all unique. It's a very powerful program, but it's all unique. And then it does have this nice little thing in here called help, where you can describe a little bit about your option. And that's why it's nice. Because you don't have to do like Perl does, where you actually have to tell it all the help stuff separately. Like I would actually argue, like let me show you here, Perl. Perl, because you're all Python people, and I'm not just shitting on Python. I'll shit on Perl here. In Perl, we do this kind of stuff here, where we say length of I equals an integer, file equals a string, verbose, and then we give it these pointers to this data to write into. That's how Perl does it, right? And this is how C does it too. It's almost the direct thing as C. But I don't think it generates help for us. See, so what you do here is in Perl, you have to say here the get options is looking to see whether or not help is set. And if it's not set, it's calling pod to usage. It's actually generating help, right, from your documentation. Let's compare that. In Perl, we generate the documentation for how the program is invoked through separately managed documentation. That's right below end, right here. What does that mean? That means every time I update the new arguments my program can take, I have to update the documentation below it. I, as a programmer, have to keep the two in sync. And if I allow these things to drift, right, now I potentially have options that aren't documented or documentation that no longer matches to arguments. Right? I have to keep those two things in sync. Python has taken it a step up from that, and it is allowing me to define the documentation for my arguments where I am defining my arguments. Now they're coupled. Kudos to Python, better than Perl. Rust is on steroids. They're not just coupled, they're the same fucking thing, you know? Your structure with all of your types in it is what it's filling in, and we provided these hints in the form of macros. You never know it, but that provides us more information for how to do this, to generate the parser for it. So you'll see here, it is generating all that help for us. Right there. That is an example of clap working in Rust, generating all that help for us. And how are we doing it? You see this right here? These ///. What is ///?
Documentation.
It's code documentation, right? It's code documentation in Rust. So in Rust, we have the notion of internal documentation // code documentation // tells Rust, I am documenting the thing directly below me. So the very same method we document Rust code is what the macro will use under the hood. By the way, it's a type-safe macro. Python and Perl don't have it. That's why they can't do this. That's why we have a trick they don't have. But the // is saying, this thing that I am documenting is right below me, and because I'm using clap, I want to use that documentation to explain these arguments. Okay? So now it's all together, and we're generating this beautiful output right here. And it supports everything. If you have a struct with another struct inside, what is that? It's a subprogram. Clap supports it. It has an abstraction for it. You just design the structure for your application's config, and clap will generate for you the argument parser entirely. I'm telling you, I like this a lot because this is a common theme in Rust. The common theme in Rust is it is a lower level language in the sense that you have direct access to memory. You can do things without reference counting or without garbage collecting. But the language itself supports higher level abstractions. So if you don't want to fuck with that shit, you're still getting a better argument parser. And I think that that's really the selling point that people miss out on when we focus on things like environmental arguments in Rust. Because no one uses that. You come from Python, your experience is arg parser, you're thinking to yourself, how is this going to beat Python? This is how it beats Python, right? And there are a ton of options here that allow you to expand on this, right? I talked about sub-programs being one of them. That's very popular, but there's all kinds of really great, amazing things that this has, you know? The value enum is another great option. If you have a struct and it declares a type, an argument like database, right? And you have an enum called databases, and you specify Postgres and MySQL, that's in your enum. And you say that this database has a type of the enum databases. Clap will tell you I have those two options. It'll tell you what those two options are, it'll generate the documentation for it. So if you want to say I have two potential values for this option, command line option, how do you do it? Create an enum. Enum, arg enumeration databases. And then give it your options, and then Clap will generate the name for it. You want to document it and say what PG is. PG is just shorthand for MySQL. Put right above it a doc comment. Say Postgres. And it'll generate that as PG, and then right next to it, it'll say Postgres. So I'm saying all of this is just natively supported. Create your enumerations, create your structs. Rust will build the entire parser for you, don't have to do shit. And it'll be strongly typed, you'll have errors. Okay, next up, I want to talk about builders. So we saw this idea of building the object, right? By the way, if anyone wants to see any of this stuff, just tell me what you want to see. I'm happy to show it off, I feel pretty passionately that this is the best argument parser in the world.
Go back to the demo.
Yeah.
So I can scroll down, keep going down all the way to the output. What name of the person to greet? Where is that?
Name of the person to greet is going to be the comment above name. So we're going to go up here to name of the person to greet. And when you run cargo doc, that struct will be documented such that name will be the name of the person to greet. So that document generates the documentation for --help, it generates the documentation in cargo doc, and it's actually written to the code, right where it should be, documenting the code too. All three of those documentation systems are now tied together. You can't beat that. No language touches it. All right, no language I've seen.
Version is magical.
What's up?
Version is magical. Version.
I don't understand. Oh, version? So version here is telling it, we have this cargo toml file. We talked a little bit about that. There's a whole list of things you can store in a cargo toml. You can store the name of all of your authors. You can store the GitHub address in which the code is downloaded from. I believe where the bug tracker is located.
So it's in the toml.
It's in the toml. It will source that information from your metadata. Now, if you don't want to source it from your metadata, say command version equals, and you can specify the version number. You want to store it in a variable or whatever? Fine, it'll work. But I'm saying by default, the version number has to be in the toml, so don't write it in two places. The macro can actually open up the toml file, read it, and populate it with your version number. -- version option will be generated, and you'll see it here too. See, so the -- version gets generated. You have that as an option. So when other people are consuming your CLI tool, if they just want to find the version option, they have the version option there. It's there for you. All right, the other thing I want to talk about is the builder pattern. The builder pattern is very popular. The builder pattern is I have an object, and I have the ability to call on it these different methods, and then I call build, and I get the object back. Why is this more useful? Well, if I have new, then I have to provide everything in arguments to the function, right? So in a normal constructor, we provide all of the different arguments to a function which does the construction for us. That is absolutely fine. There is never at any level something wrong with a constructor. However, when you get to more complex objects, sometimes you want to write more complex code. And when you have tons of options, it becomes very complex to construct an object with tons of options. Let's go back to argparse and talk about this, right? Argparse is providing this thing called add argument. Add argument could be manipulating the object you're creating, or it could be saying when you want to build the object, here's a new object argument you want to add. It could be doing either one of those two things under the hood. You're never actually building an arg parser here, so they're not using the builder pattern. But Rust does the builder pattern better than any other language too. So the builder pattern is a very popular pattern in Rust, and it is extremely good to use the builder pattern in Rust because there is no disadvantage to it. In Rust, the builder pattern gets run in compile time. So in a language like Python, Ruby, PHP, and Perl, these interpreted languages, they pay an overhead cost for the builder pattern. Because the builder pattern has to invoke a different method. There's an additional subroutine call every time you call something inside of it. And then they call .build, and now it has to look up the state and create a new object. It's just more overhead than calling a constructor. So you don't see the builder pattern used in interpreted languages much. In compiled languages, you see it quite a bit, and of them, Rust does it the best. So let's go over it, and I want to show you really quick how Rust does it. We have this thing called derive build. And derive build does the builder pattern better than anything else. Derive build, we say we want to derive, and by the way, you can implement the clap parser and the builder pattern on the same thing. They're two separate macros, code generation. And they work flawlessly because macros in Rust are done right, you know? So we have this thing here called builder, and builder looks at that struct for all of the different values inside, and it generates for you this thing called builder. It's by the same name of the struct, except it has the word builder in front of it. So we simply write derive builder, and it creates the builder pattern for us. What does the builder pattern do? It clones the struct by a different name, right? It makes the U32 an option of U32. Why? Because maybe you don't have anything there. You don't provide anything there, right? And then what it does is it gives you methods to call these things one at a time. So now we have lorem builder, and we have this function in it called ipsum. Ipsum takes a value of U32, and what does it do? It sets the internal variable ipsum. And then we call build, and what does build do? Build on lorem builder is going to return a lorem object. And how does it do it? It does it by simply calling lorem, and now what it's going to do is it's going to provide the ipsum value right here, the internal value you set. This is the code it generates. This isn't what it looks like to you. I'm just trying to show you what it's doing on the underhood. And then now we can construct lorem using this. This is what it looks like to you. So rather than providing a constructor where we have to say ipsum is 42, the next thing is 84, they're all positional, or they're all, we have to do all that kind of shit in the constructor, one function, we can do this. Now I say lorem builder, I want all the default values, I want to change the value of ipsum to 42, and I want to build it. If I get an error, bubble it up. Otherwise, give me the lorem object. That's how Rust does the builder pattern. It's one line. And it generates that whole builder for you. It's pretty cool. So now the reason why the builder pattern isn't used everywhere is because it's a pain in the ass in any other language. You have to create a builder that's separate from the thing you're building. You have to maintain them both. You have to type them both. It's a lot of work to synchronize them together, and it's problematic. In Rust, we get all of that power with a macro, and it's one line. So I'm saying this is why I think, again, Rust is the best language. It's the best language because it's a lower level language, it's faster, has actual technical advantages over all of the other languages, as far as speed, most of them anyway. And in addition to that, it has the highest level abstractions. You can't beat that in an interpreted language. You're not going to see it. You won't ever see it. OK. Those are the two things that I wanted to show. I'm happy to play around with them if anyone wants to see them. But yeah, there's a lot of really cool stuff we can do there. If we want to have something here that we don't set, we can say skip the setter. Now you don't have the ability to set it. What does anyone think of this? Does this make sense to people? Cool stuff? Are we happy?
Happy?
Do we want to see anything?
No.
Keeping it short, I like it.
But you have to, you want to create a demo part first.
Of what?
You're going to create a demo with a bunch of help documents.
You want to see the clap program? You want to play around with the clap one or the derived builder one?
The builder. Actually, I wasn't paying attention. What was the builder?
This is the builder one.
Yeah, what does it do?
It's creating the builder object. So we have this thing here. This is creating the syntax for the lorem struct. So we can say lorem builder, the default values, .ipsum42, set the value of ipsum, and then build it. Create me the lorem object. So this does all of it for you, creates this builder pattern, and all you're doing here is saying derived builder. It's creating for you a different method of constructing. That's easier than building your own constructor. And it writes the entire thing for you. Think about it. Cool. So yeah, if anyone has any questions, give me a shout. I'm happy to show you off more stuff. I like these two examples because these are things that every Rust programmer will use. The book doesn't cover them, but I feel like Rust does them the best, and it does them with remarkably little work. You know, it takes care of generating all that cool code for you.
Auto factory function generator?
It is, yes, it is a factory function generator. The builder is a factory pattern for itself.
So you don't have to write any of the code
In lorem builder. You don't have to write any of the code in lorem builder. You just say derived builder, and it makes it for you. And then you can call now this method here, which is more powerful and shorter and doesn't require you to use new or create a new. This is a different method of constructing the object that is more powerful and shorter, and it will make it for you. Yep.
Create a factory function for HTTP requests.
If you have a struct for an HTTP request, all that you would do is say derived builder, and it'll do it for you. So create your struct for an HTTP request, however you want it, and then say derived builder.
You have a cool example?
We can certainly do it. You want to do it really quick? Okay, let's give it a shot. We're going to try to create a HTTP request. So here, let's come to the top, and I'll show you how it would look. No one has to say if this isn't interesting to anyone. By all means, you can head out. But I'm going to geek out for a little bit. Let's create a struct, and we're going to call it HTTP request. And let's say that in this struct, we have, well, let's say verb, right? Because you have the verb first. Now, the verb for us, this is going to be something like this. We're going to say up here struct, and then, oh. And then this shouldn't be struct. This should say enum. HTTP verb. It's going to say something like this. Get, post, what are the others? Head, delete, yeah, whatever. Put, there we go. Now I'm going to say verb. This is going to be HTTP verb. Okay, I'm going to come up here and I'm going to say allow because I'm just doing development. Dead code. This is going to stop it from nagging me. What is it? Clippy, get contains a capitalized acronym. Oh, it doesn't like the fact that these are capitalized. Okay, fine. Put, delete, head, post, get. That's what it wants. There we go. Okay, so we have an HTTP verb. Now I'm going to need a URL, and I'm just going to call this a string for now. Sounds fine. We can make it an actual URL later. And what else do you want for this fake? Headers. You're going to make this a lot more complex. Let's skip the headers. Let's leave it as that for now, right? Because this is enough to show it off. You get the point, right?
Payload.
Oh,
I guess you can remove the
I mean, the thing about headers is now you're going to have to populate a map object, right? We can do that. Let's create this though for now. Now I'm going to do function main, and it's going to come down here, and we're going to return this. I don't think I need that. Okay, we'll say here, and then println. Okay, now we want to create an HTTP request. So I'm going to come down here and I'm going to say derive, right? And then like this. And I want to say we're going to derive the thing that we just saw here, derive builder, right? So this is the builder macro. And I need to come down into my package, and I'm going to go cargo add derive builder. Now it's adding all that stuff for me. And now, oh, I need to come up here and say here, use derive builder. Oh, that's the reason, right there. I need to have this line here to use the macros. Where the hell did the window go? Yeah, here it is. Okay. Extern create derive builder. Now, get rid of this. Put this up here. The trait bound HTTP verb is not, so what I have to do up here is I still have to say here derive clone. It needs to be clonable, the HTTP verb. I'm just reading these errors here. Oh. And now we're done. So now I can say here, right, I can say HTTP request builder. Let's come up here and say derive debug. Come up here and also derive debug, because if I derive it down there, I got to put it up here too and everything else. And
Capital HTTP?
Yes. I'm just going to say don't let it fail. And then we're in main, remember? Let's fix the color. Okay, last thing we got to do, boom, boom. Oh, I didn't give it verb. So now I need to say here dot verb, and I should be able to say here when I give it verb. I don't think that's going to work. I think you have to say HTTP verb get.
You
What?
got double dot.
Oh.
Verb.
Good catch.
Example.com.
I need to give it a URL. This is me not knowing how to use the editor.
You sure that's wrong?
There we go. No. There. And there we go. Now we created it for the HTTP request.
You make the verb optional and default to get.
Yeah, so you'll come up here, and if we want to do that, we should go IMPL. Let's see here. Oops. So we want to make it optional, so do std impl rather implement default for HTTP request. So there is no such thing as a default verb in an HTTP request, right? There is no such thing as this is what the verb should be if nothing is there. So what we're going to do is specify the default here explicitly. So now I'm going to say here self, and then I'm going to say verb is HTTP verb get. That's the default. And let's give it a website here if you don't provide it one, URL. And then I'm going to say not existent, or here, not supplied, that invalid. That's an example. But now I need to do string from. Oh, this is, I need to have here fn default. There we go. So now I have the request that's saying get, and if I come down here and I delete the verb, it still says uninitialized field verb. What? Request default URL build. That's interesting. I wasn't expecting that one. It should be inheriting the default from above. Rec HTTP request builder default. Oh, let's try this. HTTP request builder. There we go. Yeah. OK, so if we do it for the builder, we can go here. Options get, and then rather some. And then we don't have to give it a URL anymore. Now I bet this will work. No, we still have to do this. But we can say here none. No, that didn't work. Let's take a look at this. So this is the builder thing. Derived builder default. Oh, here, default values, builder. OK, that's where I'm doing this wrong. Damn it. OK, so yes, we just do this default. So if I come down here, this is not actually needed. I'm doing too much work. I come over here and I say pound builder, and then to set the default in the builder, we do default equals, builder default equals, and then I can say here HTTP verb get. That'll work. And then just change this.
Extra bracket.
Unexpected type path. Let's try that. Oh. I hate this. Someone needs to tell me how to stop that quoting thing. OK, there we go. And then here we're just going to say the default string, which we don't even have to provide. There we go. Just one of them is enough. So now cargo run. Now we're creating the request, and we have the default of get. So it's actually easier. You just provide it it for your tying the default to the actual field, and the builder does the rest. I was implementing default as if it didn't have that functionality. They have it easier now. So that's pretty easy, right? Now it's generating this HTTP request builder for us, and I say I want to start off with the default. It is generating the default for us. And then I say the URL, I'm providing a custom URL. The default verb for HTTP verb is HTTP verb get. And I say build and unwrap. And there it is. Now, there is also one that does even more in compile time, right? And it will generate it with no compile time cost. And that is called, builder, typed builder. So this is actually even better. And this one does everything, I think, in the compile time. So I'm just saying all of this stuff kind of exists in Rust. There's a lot of different modules out there that provide ridiculous code generation abilities. And a lot of people, the word macro scares them off because they've been told to hate macros. And the reason why is they're generally very hard to debug. And that's because they generally work on a text level. And that sucks. So if your macros are generating text, it's kind of garbage because you don't know what's happening until the very end or that everything happened in a sane fashion. Rust macros don't operate on a text level. They actually take the AST before them, and then they mutate the AST, and they produce another AST after them. So they're actually AST mutators. So they can do all of this kind of fancy stuff no one else can do. They don't actually parse that struct as if it was text. They get the AST for that struct, and they process on that AST. So the Rust macro that is looking at the struct implementation does not have a struct parser built into it. It is using the internal struct parser that Rust is using. So it has, and the thing that it's producing, the syntax tree it produces, also is, checked for sanity. So yeah, way better. Anyway, cool. That's all that I got. And I think we are 20 minutes short, so we're doing good on time. Ask any questions or bring them to the Rust channel. See you next week where we'll do another chapter. I think, what is it?